Welcome to my GECCO2021 talk. We want to see today how we can prove lower bounds, something that's notoriously rather difficult, in a rather easy manner. So we want to show a new method based on the fitness level method. Let's first dig into that and see what is the fitness level method. So typically we have some kind of search space that we want to explore. So let me draw it like this. We have some kind of optimum that we can see here, and we have some algorithm that's done somewhere and tries to get to this optimum. This is typically how our algorithms work. So let's look at it like this. And the search will now progress somehow and try to get to this optimum. Now, how can we analyze this progress? So first of all, we will focus on methods that will only go kind of towards the optimum in the sense that they are elitist. They will not go backwards. They will not lose quality or lose fitness. So they strictly increase only. And what we can do now is a method due to Wegener. We can partition our search space like this into many slices that lead us from wherever we start or wherever we are in the search towards the optimum. And now what we want to say is, okay, if we have a certain probability of getting out of such a slice, so this is called a level of some probability, then we can use these probabilities to bound the total time to get from wherever we start to the optimum. So since these slices are typically based on fitness, so that you can never go back a slice but always forward, it's called the fitness level method. For the method, it's not really important that it's based on fitness. What's important is that you can never go with a slice backwards. So this is not allowed. What did Wegener show? He showed that the total time it takes to get from wherever you start to the optimum is, well, in the worst case, you need to leave each level, and leaving a level, if the probability is pi, is then, because of geometric distribution, bounded by 1 over pi. And if the optimum is everything in level m, so the time it takes to reach level m, the last level, is then just this. So as you can see, we pessimistically assume here that we have to leave every level, even the initial levels that we might just skip during the start. And we pessimistically assume that we have to visit each level and that we never really skip any level. So still, this is a very powerful method, and it gives surprisingly good results on a number of test functions and is very easy to apply. I find it very convenient teaching my students these kind of methods. They can understand it rather quickly. Now, as you can see here, it's an upper bound on the runtime, not a lower bound. So it would be nice to have some kind of lower bound that's similarly easy. And so there exists a lower bound based on the fitness level method. That's due to Dirk Sudholt. So what did Dirk show? He showed that you can use some fitness level argument with viscosities. So what do we need to do? First of all, we need to take care of, well, we might not start in all the initial parts. So we only need to leave the levels where we after where we started. So this is I is the starting point. So this is the first change that we need to make. This is very reasonable. If you skip an initial level right from the outset, then of course that doesn't contribute to the runtime. And then there is a certain parameter chi here. So chi kind of accounts for the possibility to skip levels like this or even higher. So there are typically probabilities to go from this level I to a certain level j. And now the question is, what's the probability to even skip higher than j? And for this we have this parameter chi. So essentially you can think of chi as a uniform lower bound, so uniform over all possible choices of I and j, to go from level I to level j and not higher. So if we condition on going at least to level J, like this here, at least to level J, and if we go at least to level J, then conditional on that, we need to arrive at level J and not skip it with this probability chi, or at least this needs to be a lower bound for this. So if we have such a lower bound, this is called the, I forgot what it's called. Anyway, this is with viscosities. Then we can have this total lower bound here. And this Dirk already used to show some nice lower bounds for various applications. But still, getting this chi parameter right and the details you can find in his paper, it is somewhat intricate. Now, what I want you to remember is that we have two different ways of accounting for skipping initial levels and of skipping later levels. Now, I want to talk with you about our bound. So in our bound, we unify these two ways of skipping levels, and we just say that, well, basically we only need to leave a level with this probability pi, and then taking a time of 1 over pi if we are in this level at all. So if during a run we visit this level. So for this we have visit probabilities. If this is now level I, we have a visit probability vi. And we have such for every level, of course. And now we have a fairly clean theorem that says the expected time to reach the optimum is exactly, if you know the visit probabilities and the leaving probabilities exactly, this quantity. So you have to pay the 1 over pi, so to speak, the time to leave a level exactly only if you need to leave this level. I mean, if you visit this level, and otherwise you don't. So, of course, in the paper we have versions for upper and lower bounds, depending on whether we have upper or lower bounds, and lower and upper bounds for the pi and vi, that you can all see in the paper. But so this formulation, if you know everything exactly, then you know the exact runtime. And of course, it's just as useful for bounds. So with this, we account for skipping early levels by starting here, because that just means that these visit probabilities are correspondingly low. And we also account for skipping levels here. And still, these PIs just need to be probabilities to leave to any higher level. It doesn't need to be the probability to leave to the next level or something, just any higher level is fine. So this gives us this very easy way to bounding here the search. Let us now look at straightforward application. So one straightforward application is the 1 + 1 EA on LeadingOnes. You could even say that our bound is a generalization of the proof that is already long known for the 1 + 1 EA on LeadingOnes. So, but first, what is LeadingOnes? LeadingOnes is a fitness function. You can look at a bit string, and however many ones are there in the beginning is then the fitness value. And now the 1 + 1 EA tries to optimize this, and it has a bit flip probability. So in each iteration, we flip each position, including the ones that are already optimized, with probability p independently. And then we hope that we get something better. If we get something better, we accept. If we get something worse, we reject. And if it's a tie, then we typically also accept. So how can we analyze this algorithm now? Well, with our fitness level method. So we need to say what are our fitness levels. And level I has I leading 1. So it contains all the bit strings with I leading 1. So this would be in level 3, like this. And of course, all other bits would also be level 3. And then the optimum would be the sole bit string with n leading 1, so with exactly n ones, and would be in ln, and nothing else would be in ln. We now know that we have visit probabilities for each of the different levels. So this is due to previous work that showed with some calculations. It's also not too difficult, but it's an ingenious application of some kind of symmetry, that we have visit probabilities of 1/2 for each fitness level, and these are exact probabilities. So it's not just an upper or a lower bound. It's exactly 1/2 that we visit a certain fitness level. And now we need the leave probability. So the leave probability is the probability to get a better offspring. And to get a better offspring, we should not flip one of our leading ones. So all these I leading ones we should not flip. And then the next 0 we should flip in order to get better fitness. And then the fitness might be better by 1 if the next then is a 0. So if this would, for example, also be flipped while this was flipped. Or it might already be 2 more if this 1 stays, or even more. So this doesn't matter. It's better. So that's the leave probability Pi. Now we can just take it all together. So this is the visit probability, since they are all the same. I can take them in front of the sum, and the rest is just 1 over the leave probabilities. And since we have a level 0, our level start at 0, we go to 0. And since we have n as the level which contains the optimum, we go to n minus 1. And this is, of course, already known that this is the expected time. You can now compute this sum if you want, or estimate it and get lead constants and so forth, or plug in the p that you prefer, for example 1 over n. So with this formula you can do all kinds of things, but for us of interest is just that we can use our fitness level method with visit probabilities to get this accurate runtime rather quickly and easily. What further applications do we have? We can look at the 1+1 EA on OneMax. You can find the details in the paper, but OneMax is generally you have some bit string and you count the ones, and this is your fitness. So this is now, let's say my bit string ends here, not ... otherwise I can't say. That would be 3 again. And then just as before, the 1+1 EA flips bits, each bit independently with probability 1 over n. We just now did this analysis. This is one of the key test functions. You can find the entire analysis in our paper. There are plenty of results and improvements of such results, of course, out in the literature. But we easily somewhat derive with our method something that has the correct lead constant, and then in the constant of the order n term they differ slightly, and this is already very accurate. And then there are some kind of further error terms, of course. This is wrong. Sorry, that wouldn't make any sense if there's order 1, order n. So this is order 1. Sorry for that. Yeah. And of course you can find better bounds in the literature, but they use much more involved techniques and are more difficult to explain. In the paper you can also find one more application on long k-paths. They are again somewhat more easily understood, but finding a lower bound here is also somewhat tricky due to the algorithm's ability to take shortcuts. So you can find all these details in the paper. What did we see overall? We saw a new technique for showing lower bounds. So this is what you can take away from this. It's easy to understand, easy to apply. Use for students is highly recommended, especially master students in some kind of courses. It gives surprisingly tight results, depending, of course, how accurately you can find the visit probabilities and the leave probabilities, as is always the case. But after that, you can just plug it in and get the formula right out. And the core limitation is that it only applies to elitist algorithms, so you need to go forward through the search and never backwards.